a formula we wrote down last time without justifying. We won't justify it today, but we will convince ourselves of its veracity by graphing. So, from what we did last time, by looking at a few pages previous in your notes, what is the sine of the inverse cosine of x always equal to? What's the formula we wrote down for it? Oh no, we totally did. Okay, I'm sorry. So we wrote down a formula for the cosine of inverse sine of x. Got the square root of 1 minus x squared. So I'm going to go back and put it in the place in the notes where it belongs. Sorry, I thought that we had done that. Sine of the inverse cosine of x is the square root of 1 minus x squared. Let's think about the cosine of the inverse sine of x. Do I have that in the wrong spot for what I just said? Okay. Well, I guess theoretically I should erase this, but if you wrote it down, don't erase it. Yeah. Cosine of the inverse sine of x is the square root of 1 minus x squared. And we got that last time. We did that by studying some right triangles. And we did somewhat with the other permutation of that, the sine of the inverse cosine of x. So I'm not going to do it right here. The same ideas we did last time, we'll let you do it. Here's a formula. The sine of the inverse cosine of x is the square root of 1 minus x squared. The exact same thing as we got for the other order of these. So, I'm going to put that on that previous page. The sine of the inverse cosine of x is the square root of 1 minus x squared. And the idea needed to get that formula is just draw a right triangle. That's all you need to do. I don't want to spend time on getting that formula right now, so instead maybe I'll try to convince you of it this way. Do you think you can have a calculator, have a computer graph this and graph that and see how it looks? Let's graph the two things, see how they look. Sine of cosine of x. There is the graph of sine of the inverse cosine of x. How would you describe the shape of that graph? It's kind of a circle. It's the top half of the circle. I guess these all are going to have the same formula, so let's also compute the cosine of the inverse sine of x. Is that the same again? Alright, so I believe those two should be equal. Let's get the square root of 1 minus x squared. That would be the same again? Nice. So let's think about maybe just briefly why each of these should give half of the circle. And let's start with that one. So how do you read the instructions that give this? So these say start with an x value, then we're calling the simplest angle that gives you that x value. And then sine is going to read off the y. So what this is saying is start with an x value on the unit circle. Find the y value that corresponds to that x value on the unit. Okay, I just described points on the unit. So that's why this should be the graph of the circle. And it's the graph of half the circle because of the step we picked the simplest. Same thing for this, but backwards. This time the input I'm getting, the x value I'm getting is the y value on the unit circle, even though it's a horizontal scale. And then find the simplest angle that gives you that y value, then I'll probably the x values. And why is that the same? Well, x squared plus y squared is the distance formula, so it should be 1. Solve that for y and you get this. So there's one very brief explanation for how it should be the same. Well, let's use the ideas we got to get this formula, and let's use it to do one more computation. Let's try to compute the cosine of the inverse tangent of negative 4 over 5. So remember the way that we think about this. Inverse tangent of negative 4 over 5 is an angle. It's the simplest angle whose tangent is negative 4 over 5. So if theta is the inverse tangent of negative 4 over 5, then I know the tangent of theta. The tangent of theta is negative 4 over 5. So what this problem is asking is if you know tangent, can you look up our cosine? Can't you? Let's try to look up our cosine. Let's start with a few pictures and start with Kazuka. And do this also picture and then I'll write mine. So, let's start with this. What quadrant is this angle in? So if tangent is negative, because it's negative 4 over 5, could this angle possibly be in quadrant 1? No. Tangent is positive in quadrant 1. Tangent is bigger than 0 in quadrant 1. This angle could not be in quadrant 1. Could this angle possibly be in quadrant 2? So it could be in quadrant 2. Maybe I'll highlight that with blue because it's possible. Could this angle possibly be in quadrant 3? No. In quadrant 3, tangent's the slope, right? There's a line with positive slope. So it couldn't be in quadrant 3. Could this angle be in quadrant 4? Yes. So this angle is in either quadrant 2 or quadrant 1 just because tangent is negative. But what's the length of inverse tangent? Look back a few pages. Or picture the graph of tangent. Negative pi over 2, pi over 2. Ooh, I'll write something that's wrong and you'll tell me why it's wrong. Did I write that down correctly or incorrectly? What's wrong? Endpoints are excellent, right? Inverse tangent has these horizontal asymptotes. It doesn't ever actually hit the value of pi. Neat. What quadrants do those angles trace out? I caught some right things, but it was very quiet, so I want someone to say it with confidence. What quadrants does that trace out? 1 and 4. And it excludes the axis, so I'll indicate that with So what quadrant is this angle actually in? Quadrant 4. So all that work that we just did tells me that the inverse tangent of negative 4 over 5 is in quadrant 4. Let's draw a picture of this angle then. It's in quadrant 4. And I know for a fact that the tangent of this angle is negative 4 over 5. So what sides of this right triangle that I just drew could I label? Opposite and adjacent. How should I label them? I'm fine with that ball being there. I think I'm happier with the minus ball being there because it's like I get that it's the side of a triangle, so maybe you should indicate it as just 4 because that's the line. But I want to remember that it's pointing down. That's not a super important. So what's the hypotenuse? I hear a square root of 41. Anyone disagree? Anyone want the hypotenuse discussed? That's right, yeah. See, it's the square root of the square root. So now that you have this written down, can you compute the cosine of this angle? What's the cosine of this angle? So cosine of the inverse tangent of negative 4 over 5 appears to be 5 over the square root of 41. That is correct, but it's not simplified. How should it be simplified? Yeah, you can have a square root of the denominator. That's allowed, but it's not maximally simplified. So how do you get rid of the denominator? multiply and divide by square root of 41, giving you 5 root 41 over 40. And the useful reason to do that is if you make sure you never have any square roots in the denominator, it's easy to tell two numbers. Easy on. How do you feel about that idea? Feel pretty okay? While we're here, let's get some low-hanging fruit. What if I asked you to compute the sine of the tangent inverse of negative 4 over 5? Using this same triangle, do you think you could compute it? What would you get? Yeah. Nice. Cool. In fact, do you think you could do this for basically anything that you could put inside of those parentheses? I think you just put an x inside of those parentheses, you could follow through these steps with some variables on the triangle instead and get an answer. Get like a formula for what this is? If so, then you may be entitled to extra credit. The extra credit that appears next in the notes is to get a formula for exactly that. And on the one hand, the formulas aren't secret, they're out there. You can find a formula for what this is. It's in the book. But I want you to come by my office and explain where that formula comes from. Draw some triangles. I'm talking to you. And people think they might do that one. That's. In particular, if you don't like how today's quiz went, a single extra credit will more than make up for a 0 on a single quiz. That's how the quizzes are long and how much the extra credits are. You know. So, with my very small amount of remaining time, my remaining 10 minutes, let's remember why we care about inverse trigonometry. The reason we gave to care about things like log functions is they let you solve exponential equations. The reason you care about square root functions is they let you solve equations that have squares. The reason we care about inverse trigonometry is because it's the tool we need to solve trigonometric equations. So let's solve some trigonometric equations. I think with my 10 minutes we have enough time to do at least one in full detail. Let's solve the following equation. Cosine of theta equals 1 over 30. Let's solve that equation. And as a bit of motivation, let's just try to convince ourselves how many solutions there should be. Here's the graph of cosine of x. There's the graph of y equals 1 over 30. By looking at this picture, how many solutions would you say this equation should have? Excellent. Right, yeah, that picture only goes so far. I really think that it's going on forever. There are infinitely many solutions. Infinitely many solutions. So that means that whatever way I find of writing the solution, there will be like something that gives it infinite family functions. Right, since this is twin function based, I think I'll find you like plus 2 pi. If I find one solution, then I can add 2 pi to get more solutions. Yeah, 4 pi, 8 pi, and so on. So let's try to find some solutions. So there's one solution that inverse trigonometry just gives me. So I want angles whose cosine is 1 over 30. What's the name for an angle whose cosine is 1 over 30? You aren't so high to call inverse cosine. So what seems like, so one angle whose cosine is 1 over 30 is inverse cosine of 1 over 30, right? Oh, sorry, your hand was up. It's not very far. Is that what you were going to say? Oh, okay. Well, better than nothing. So let's just, so So like the point of inverse trigonometry is that inverse cosine of anything is an angle with cosine equal to that thing. That W slash is supposed to be a width. So whenever you want to solve cosine is equal to inverse, you know a solution. Inverse cosine of that number is a solution. How could you get, so another note is like, that's the solution that lives between 0 and pi, right? So, that's like this solution, I think. Is there 0 up to pi? So we just found that solution. This graph is going to get pretty ugly by the time I'm done with it. So that solution is x equals cosine inverse of 1 over 1. Alright, so we just found a solution. Sorry, I'm off page. How can we find more solutions? Oh. How about add 2 pi? Yeah, you can add 2 pi to get another angle that has the same x value. Take this angle, add 2 pi. That'll get you there. How could you get more solutions? Add another 2 pi. You could say subtraction 2 pi. I guess that's the same as adding negative multiples of 2 pi. So that'll give us one infinite family of solutions. Theta equal to inverse cosine of 1 pod plus 2 pi k. And maybe I'll go ahead and draw a little bit more of the graph and highlight those solutions. Am I missing any? I'm missing like half of them. So I think if I find one other solution and then play the same add 2 pi k game, that will give me all of them. In fact, I think there's maybe a reasonably simple representative of a mathematics. Not negative 1 bar, you have to have like a wall. Negative inverse cosine. So another solution, let's use the fact that cosine of negative theta is the same as cosine of theta. Sorry, that looks like I highlighted what I meant to like cross out. So we can get a second solution in the form negative cosine inverse of 1 over theta. Now that I found that second solution, can I start adding 2 pi's to that and get more solutions? Look like I'll get all the solutions if I do. Nice. So if you want all the solutions, I think it's cosine inverse of 1 third plus 2 pi k, and negative cosine inverse of 1 third plus 2 pi k. Well, I guess you could write this all in one line. It's either plus or minus that thing. Plus or minus cosine inverse of 1 over 3 plus 2 pi k, where k is any positive on it. How's that make you feel? It seems sensible now? So, with my remaining 2 minutes, I think I'm going to skip a little bit of the content. We'll come back to it next time. I want to jump to a flow chart which will summarize all of these ideas. So, flow chart. Let's suppose you want to solve cosine of x is equal to a number. The general case, which is labeled as the standard case, if this number c is between negative 1 and 1, then the steps you should follow are step 1, find the simplest solution, namely cosine inverse of whatever that c is. Right, whenever one asks you to solve cosine of x is equal to a number, take inverse cosine of that number, that's a solution. We just not have to find a second solution. Stick a negative in. Next, once you find those two solutions, add 2 pi k's to get all the solutions. So that's like the generic case. If someone gives you most situations of things that you can solve, there's a way to go. You should simplify if possible, but I think I don't want to emphasize that right now. What if I give you something bigger than 1? What if I I ask you to solve what's the solution to cosine of x equals to 253? What's the biggest cosine can be? Is cosine ever equal to 253? What's the solution to cosine of x equals 253? So it's not a there are no solutions. So if c is bigger than 1, there are just no solutions. If c is less than 1 in absolute value, then you can find solutions. Here's how to do it. If c is equal to 1, well, let's maybe even just see if we can't root it off. So cosine is the x value. What's an angle that gives you a cosine of 1? 0. What's the next angle that gives you a cosine of 1? 0? 180 would put you there, and it's in degrees. I think 2 pi, or 360 if you like degrees. What's the next solution? Around this all again, is that x equals 1? 4 pi, 6 pi, 8 pi. What if you want to get to x equals negative 1? I'm bringing that to what 180 if you like degrees. Pi because I like degrees. In fact, is that point the only point on the unit circle where x is equal to negative 1? So that's the only solution, and then you add 2 pi k's. So there's a complete flowchart for solving simple cosine equations. What we'll get into next time is sine and tangent, and then how to use that. So, as you'll remind you, this class is not happening for the next 2 days. Really the next 4 days, but I don't think I need to tell you that. I don't think Saturday or Sunday. I mean, I've been showing up here Saturday or Sunday, right? You could. Maybe not Sunday. I think the building's not on Sunday. So anyway, enjoy it and talk. Also, be doing things like answering emails and have questions for you. I'm not planning on having office hours the next 2 days. I'll have my day office hours. If you really want to see me in person, shoot me an email and we'll figure something out. See you. See you.